Let's look a little bit at our modern physics unit here too, what are called energy level diagrams. Get so. All right, one for hydrogen, one for mercury. There are others, of course. What you need to be able to talk about here are two things. One, that electrons can make transitions between energy levels. These are what are called the quantum number, or the state number of those energy levels. So that hydrogen has state 1, state 2, or level 1, level 2, level 3, level 4, blah, 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 blah. Okay? So those are the number of each state, and the energy of each state is listed on this side in what are called electron volts. All right? So for example, let's say we have an electron in the n equals 2 state. Well, if that electron does what we call decays back to the ground state, that electron has undergone a change in energy from that to that. And what happens in that case is that the atom does this. This is what we call an emitted photon. Photon is a light particle, or a bundle of light energy. Okay, now this photon has an energy that's equal to the difference in those two energies. And I'll put absolute value. I don't care about signs. I wouldn't worry too much about signs here. Notice the change in energy between these two is 10.2 EVs. So this photon would have an energy of 10.2 EVs. Exactly the difference between those two energy states. Now, that energy is related to the photon's frequency by that equation E equals HF. Now, what you need to be able to do is if you wanted to find the frequency of that photon, you'd use H, which is Planck's constant, which is measured in joule seconds. So you need to find this energy in joules. And here's how you do that. Well, let's see. I want to get rid of EVs. I want to end up with joules. The conversion is 1 EV, by definition, is 1.6 times 10 to the negative 19th joules. EVs divide away. We're left with joules. Wonderful. And now we could find the frequency of that photon. Okay? Now, the other thing we can do is if we kick in, or if a photon has just the right energy, it could potentially make this electron, we'll say this is excited. We could excite this electron and make it go from state 2 to state 4. So this is what we would call an absorbed photon. Now, it has to have exactly the right amount of energy, and that energy has to be, let's see, the same as the difference in energies of those two states. So the difference between 3.4 and 0.85, if my math is right, and it usually is, would be exactly 2.55 electron volts. All right? We had 2.54. That's not enough energy to get it there. We had 2.56. That's too much. And we don't just take out the 2.56 or 2.55 and leave 0.01 EVs of extra energy just hanging around. That doesn't happen. All right? So hydrogen can only emit or absorb very specific energy photons, and therefore very specific frequency photons. And frequency for light has to do with color. So that's why hydrogen has what we call an absorption spectrum and an emission spectrum that show you what colors that correspond to frequencies, that correspond to energies, hydrogen can absorb and or emit. But only those. It can't absorb or emit anything at once, only very specific ones. Okay? Another thing to be familiar with is that, let's say we have this electron in the n equals 4 state. I know it says 5 right here, but look, 2, 3, 4. Right? If this electron is going to go back to n equals 2, it could do it in in 3 ways. One, it could first do this and then do this, or two, I guess that's 2 ways. 2, it could go all the way there. But notice there are 3 different transitions that could happen. Right? Here's a transition, 4 to 3. Here's a transition, 3 to 2. Here's a transition, 4 to 2. Those are 3 separate transitions. You ought to be able to identify that. Okay? That there's more than one way to go from 4 to 2. All right? So that's a little look at spectrum stuff. Now, as I said, we could find the frequency of this photon. If we were to do that, we could then look at a different part of the reference table. That stuff all stays there. That stinks. We could look at this, and what we could find, sorry, that's a mess. We could say, well, all right, if this thing has a frequency of, I happen to know it's a pretty big frequency. Let's say that this frequency comes out to something times 10 to the 15th hertz. Well, what you ought to be able to do is say, oh, okay, well, anything in the 10 to the 15th, hang on. I'll just erase. Yeah, if this thing has a frequency, we calculate it to be something times 10 to the 15th hertz. Well, look, these are frequencies. And here's 10 to the 15th and up. Well, those are all ultraviolet. So you could characterize any of those photons based on their frequency. Okay? You also, some of the questions might very well ask you, once you calculate a frequency, it'll probably be in this range, and they'll say, okay, what color light is that? So you ought to be able to recognize that, A, these are frequencies, and based on what value you get, figure out what color that photon is. All right? Now, the other thing about this, the electromagnetic spectrum, is that these are all just different varieties of that. All right? Light is part of the electromagnetic spectrum. All these waves, different kind of waves, are electromagnetic waves. And electromagnetic waves means that. So for any of these, what you'll notice is if you take the frequency and look at its corresponding wavelength, well, they're related like that. C equals F lambda. You could take any one of these, I don't know, let's say wavelengths, and if you wanted to find the frequency, you take C and divide by that wavelength, and you'll get the frequency. All right, they all differ by a factor of 3 times 10 to the 8th. So just remember, any of these, all of them move at that speed in a vacuum or in air. Okay? They're all the same kind of wave, just with different frequencies and wavelengths. Okay? Okay.